Yeah, so today's section is a section that was going to go back and we're going to review some limit ideas because we haven't talked about those in perhaps too long. Reviewing limit concepts today. Direct substitution is always your first weapon to pull. Indeterminate forms, often you get an indeterminate form from direct substitution, so we have ways of addressing that. And one of those ways is going to be a new concept we talk about today called L'Hopital's rule. I know it looks like La Hospital, and in fact, some texts do put an S in there. It literally would be La Hospital, except in either event, you don't pronounce the S in this French mathematician's name. So L'Hopital's it is. So before we get to the new stuff, let's review some limit ideas. Here we have a graph, an exponential graph. The function for it is given up here. And they're asking us, what's the limit as you go, as x approaches negative infinity? There is a negative sign in there. Well, as this graph goes forever to the left, we can see there appears to be a horizontal asymptote when x is 0. If you were to plug in like negative 1,000 in for x here, you would see you're getting like 2 over a very large number. 0 is going to be the limit as a result. How about as you approach the x value of 0? Well, if you look at the graph appears to go through 0, I don't know, maybe about a half. It's hard to tell exactly from a graph what fraction that is. So let's go right to the source. Let's go to the function. Let's direct sub 0 in for x. We would get 2 times e to the 0, which is 2 times 1 on top. And we would get 0 plus 4, which is 4 on the bottom. Sure enough, it is a half that the graph's limit is as you approach 0. Finally, as you go off to the right, you can see the graph is diverging, they call that, when it's not limited by a number at all. I think the AP test generally will allow you to say does not exist here. If you want to be a little more specific about it, you can say specifically it's going to positive infinity as opposed to negative infinity. Now let's pretend for a minute we didn't have that graph. All we had was the equation. How could we have found the limits if we had only been given the equation? There it is. Truth be told, we already kind of addressed that doing A, B, and C. To be a little more formal about it, in A, if we wanted to plug in negative infinity, we'd have something like that. E to the negative infinity would be like e to the positive infinity on the bottom, because if you have a negative exponent in a monomial, you can move that to the denominator. Negative infinity squared would be just infinity again. So you'd have e to the infinity times infinity. You'd have a constant number being divided by a very, very large number, an infinitely large number, and that would give 0 as a result. Because if you chop 2 into infinite pieces, each piece will be literally 0 units large. With B, we just did direct sub. We said 2 times e to the 0 over 0 squared plus 4 gave us 2 over 4, gave us 1/2. And for C, if we were to plug infinity in, we'd have 2e to the infinity over infinity squared plus 4. You have infinity over infinity. That's an indeterminate form, just like 0 over 0 is. So we would have to do something else. We could, for instance, divide every term in this problem by the greatest powered term in the problem, which would be infinity. So I'm going to divide everything by e to the infinity. we would get 2 on top. And then infinity squared versus e to the infinity, having an infinity power is going to give you a greater result than having infinity as your base, as ridiculous as this sounds. Which means you'd have, you'd have a 0 for this term, because the denominator of this fraction is far, far greater than the numerator. So as the x values got larger, the bottom would become much larger than the top. 4 over e to the infinity would be 0 as well. You get 2 divided by 0. That result does not exist, which is what we found off the graph as well. And this is going to actually be, this kind of problem will be a great candidate for L'Hopital's rule. It's going to help us sort out, what is greater, e to the infinity versus infinity squared. Well, one is actually a greater magnitude than the other. And L'Hopital's rule is going to help us sort of bypass that whole philosophical conundrum. So yeah, indeterminate forms, the ones we are most used to are for sure 0 over 0. We dealt with that all the time early in the year. And infinity over infinity, we dealt with that a lot when we had rational functions. But there are other ones. 0 times infinity is also an indeterminate form. Infinity minus infinity is an indeterminate form because infinities can be greater sizes than another. For instance, the number of even numbers is infinite. And the number of integers is also infinite. But surely there are more integers than there are even integers. Even though they're both infinite, one of these infinities is of a greater magnitude than the other. So that's why infinity minus infinity isn't necessarily 0, because you might not be playing with the same quote-unquote size of infinities. So without getting too much into the weeds with this, maybe we already have gone too far into it, that's just sort of the general idea, though, of why you can't assume infinity divided by infinity is 1, or infinity minus infinity is 0. So that brings us to L'Hopital's rule. L'Hopital's rule is a way to evaluate limits where direct sub yields the kind of the familiar 0 over 0 or infinity over infinity. Though it can be finagled to work with other indeterminate forms as well. Generally, we're going to mostly be focusing on 0 over 0 and infinity over infinity. So L'Hopital's rule is set up with the idea that you have f of x over g of x as your function. It's going to be, that means it's a rational function. You have a numerator and a denominator here. So they're breaking the numerator and the denominator up into 2 separate functions. So the interval is going to go from a to b in all of these. C is going to be something in between. F and g need to be differentiable in order for this to work. And the derivative of the bottom cannot be 0, because you don't want to be dividing by 0. And you have, this is important, direct sub has to give you an indeterminate form. If you don't get an indeterminate form using direct sub, then you can't use L'Hopital's rule. But that's okay, because if direct sub doesn't give you an indeterminate form, that's just your answer anyway, and you wouldn't need L'Hopital's rule. But the point is, you always want to start with DS. Start with direct sub, because that's going to be your path of least resistance if it actually works. If it doesn't work, it's going to verify that you should try something else. So that takes us to the punchline, and I got so excited I tried to write it twice originally. If you have a rational function, you plug c in to try to find a limit, and you get an indeterminate form, then what you can do is you can take the derivative of the top as a separate function, the derivative of the bottom as a separate function, and plug c into that result and see if you get a new value, like an actual not indeterminate form. If you do that, the limit for this will be the same as the limit for the original function. So L'Hopital's rule is actually kind of like the quotient rule that people would make up for themselves if the quotient rule didn't exist. So like when we first started doing quotient rule, and this is why I don't like teaching L'Hopital's rule early in the year, if you have a function like this, and I say, hey, what's the derivative of this function? Before we talked about quotient rule, people would probably just assume, well, you do derivative of the top, and you do derivative of the bottom. And that's wrong. That's not how you get the derivative of y. You use quotient rule. But with L'Hopital's rule, it works. You would just take, like, you would take the derivative of the top and the derivative of the bottom. It's like doing the quotient rule the wrong way. That's how L'Hopital's rule works. But it gives you something completely different than the quotient rule does. All right, so we want to apply L'Hopital's rule to part C on the previous page. Let me find that. Where did I put that? There it is. If we try direct sub, and we did that on the previous page, we got infinity over infinity. That is an indeterminate form. That's the validation that we need to be able to use L'Hopital's rule. So I'm still going to put my limit out front because I am still evaluating a limit here. The function that we're going to write here is not equal to the function here, but their limits are going to be equal. Big distinction there. To do that, I'm going to take the derivative of the top. So 2e to the x has a derivative of 2e to the x. And I'm going to take the derivative of the bottom. That's just going to give me 2x. I'm going to try direct subbing then into this. I'd still have infinity on the top, and I'd still have infinity on the bottom. But that's okay. You can use L'Hopital's rule again. Now let's take the derivative of the top. We still have 2e to the x. And you can see that this numerator is not going to relent in its infinity state. But the denominator is. It's a polynomial function. So every time it's dropping by a power of x. And eventually it's going to drop to just a constant. And then when we get to direct sub, we still have infinity on top, but now we have 2 on the bottom. Infinity over 2 is really infinity, which means the limit does not exist. And that we found that both on the front with the graph and also by dividing every power by the greatest, or dividing every term by the greatest power in the problem. So for part E, and this is a little bit like what a lot of your homework problems are going to look like in this section, they want you to find the limit 2 different ways. And no matter what technique you're using, you should make direct sub your first step. If we plug 2 in, we get, or negative 2 in, we get 4 times 4 is 16. On the bottom we get 2 times 4 is 8. We get minus 10 plus 2. Sure enough, we get 0 over 0. So one way to find this limit would be with L'Hopital's rule. We're going to do the limit as x approaches negative 2. Take the derivative of the top and you'd get 8x. Take the derivative of the bottom and you'd get 4x plus 5. And then direct sub would give us negative 16 on top and negative 8 plus 5 on the bottom, which looks like negative 16 over negative 3, so 16 thirds. Now, before we had L'Hopital's rule earlier in the year, we would try something else in these indeterminate situations. And what we could try here is factoring. We can factor a 4 out of the top, and the bottom should unfoil. Now look, I see that this is a difference of squares, so we're going to have an x plus 2 and an x minus 2. Which means one of these factors on the bottom is probably going to have to be an x plus 2 or an x minus 2. It's not going to be this one because I already have a 2 here, so I wouldn't also have a 2 here. I'd be able to factor something out. So my 2 almost has to go there, which means I need a 1 here to multiply to it. And I need to make 5 in the middle. So I guess these are both positive. 4x and x would give you 5x. So we've really got 4x plus 2, x minus 2. I'm really still doing the limit of this. We've got 2x plus 1 and x plus 2. These factors make 1 when you divide them. And so if I direct sub into what's left, I get 4 times, this is negative 4. And on bottom I get negative 4 plus 1. And I get negative 16 over negative 3 again. So this is the old way we found these limits. This is L'Hopital's rule, that's the new way. You should obviously get the same thing using either technique. Another couple examples on the back, or on the next page. The same idea on the back. We always want to try direct sub as our first line of defense. If I do cosine of 3 pi over 2 and sine of 4 times a half would be 2 pi. So 3 pi over 2 is the bottom of the unit circle. The cosine value there would be 0. 2 pi is the rightmost point on the circle. That would be 0 as well. So if I'm going to do L'Hopital's rule on this indeterminate form, I'm still going to write my limit out front because I haven't evaluated a limit yet. Derivative of cosine 3x. So derivative of cosine is negative sine of the same angle, and then we chain on the derivative of the angle. On the bottom, derivative of sine is positive cosine of the same angle, but then we chain on the derivative of the angle. And if we use direct sub on this new function, sine of 3 pi over, or negative sine of 3 pi over 2, and on bottom we have cosine of 2 pi. So at the bottom of the unit circle, your sine value is negative 1. Then we're going to make that negative, so it's positive 1 times 3. And on the rightmost point on the unit circle, the cosine value there is 0 times 4 is still 0. So that would imply the limit does not exist. So for this problem, it doesn't say to find it 2 different ways, so we're going to let it sit there. In G, if we try direct sub on that, we get 3 squared is 9 plus 2 on top. Ooh, that's not going to be indeterminate. On the bottom, you get 9 plus 8 is 17. So you get 11/17, and that's it. Always do direct sub first, folks. Last problem. If we try direct sub on this thing, we get infinity times natural log of 1. Hold on. Infinity times natural log of 1 plus 3 over infinity. That's like saying natural log of 1 plus 0, because 3 divided by infinity is going to give you 0. Chopping 3 up into infinite parts means each part is 0 units wide. So we have infinity times 0, which is, of course, or maybe not of course, but it is one of those sort of obscure indeterminate forms that we talked about on the first page. So L'Hopital's rule is set up to deal with these, but you have to get your equation into rational form in order for L'Hopital's rule to work. So let's do a little rearranging of this problem. So I'm going to go back to the original problem, and I'm going to write it as a rational function, or at least as a fraction. So instead of x times this natural log, I'm going to leave the natural log part as the top of my fraction. And then instead of multiplying by x, I'm going to divide by the reciprocal. Often when we're dividing by something, we say we think of it as multiplying by the reciprocal. Well, it works the other way around. Instead of multiplying by x, I'm going to divide by its reciprocal. And the whole purpose in doing that is to set up something in f of x over g of x form so I can use L'Hopital's rule on it. So now I know this gives me an indeterminate form. I've already established that. It was written differently, but it's still equivalent. So I'm going to do the derivative of the top. Derivative of natural log of a quantity is the derivative of the quantity over the original quantity. So the derivative of 1 plus 3 over x is going to be 0 plus something. The derivative of 3 over x, which by the way could be called 3x to the negative first, the derivative then would be a negative 3x to the negative 2. And that would be like negative 3 over x squared would be the same thing. So the derivative of this is this, and then putting it over its original self gives you the derivative of the natural log quantity. On the bottom, we just need to do the derivative of 1 over x, which is like x to the negative first. Well, the derivative of that's going to be negative 1 x to the negative second. So you'd get negative 1 over x squared. So this is the first iteration of L'Hopital's rule. Let's see if we can clean this up at all. I'm seeing that we're over x squared here and we're over x squared here. I wonder if we can tidy that up a bit. So I'm going to write this as 3 over x squared over 1 plus 3 over x. Instead of dividing by this fraction, I'm going to call it multiplying by the reciprocal. So I'm flipping this and making it a multiplication problem. Then this is over x squared. I could really just put that into the denominator since it's already in the denominator of the top part of the fraction. And by doing that, it would cancel, quote unquote, cancel the x squared on top. And to clean up what's left here, I'd just have a negative 3 in my numerator. I'd have 1 plus 3 over x in the bottom with a negative 1. This negative and this negative would make a positive 1. And if I direct sub into what's left, I've got 3 on top, and I've got 1 plus 3 over infinity on the bottom. That's going to be 1 plus 0, which would give you 3 overall. I'm just going to double check this really quickly on decimal, so I'm going to make a graph of the original function. Yeah, and the graph makes a pretty convincing argument that as we go off to infinity, 3 is a reasonable looking limit. If I zoom out, I mean. Sure. So just to recap and review, always, whenever you're doing a limit technique, make direct sub your number one choice. If that doesn't get you an answer, there are the other techniques. Some of the other techniques you can try are analyzing the graph, if you have one. Make a table of values that are really close to C on either side, and see if the values are the y values are approaching the same number on each side. Factor and cancel like we did in the example earlier in these notes. Rationalize the numerator if you have a square root in the numerator. Sometimes that'll work. Trig theorems, remember that as x approaches 0, sine of x over x becomes 1. the limit. And as x approaches 0, 1 minus cosine x over x becomes 0. And then L'Hopital's rule if you have an indeterminate form as well. On the homework, they're going to ask you on a lot of the problems to show an old technique along with L'Hopital's rule. These are really good techniques to show in those problems. So give them a shot. Let me know if you have trouble. Thanks.